Welcome everyone. In today's video, we will understand the concept of finite element analysis and its uses and needs. The topics of this video is as follows. We will first look at the methodology for modeling any physical system and their examples, and then we'll look what is FEA, why to use FEA, and when to use FEA. Now, let's start by understanding the modeling of any system, which is essential for engineer. All natural phenomena and physical systems can be mathematically modeled as, differential equations. While some differential equations can be solved analytically and will have exact solution, most of the differential equations can't be solved analytically. Thus, engineers and mathematicians have found out ways to solve these complicated differential equations, which are broadly classified as numerical methods that give approximate solutions to these differential equations. Finite element method is one of the numerical methods which uses variational method to convert the differential equation into a system of algebraic equations. These equations are further solved using computational techniques. Let's look at a few examples of the physical systems. In our day-to-day life, there are instances where we assume a certain machine is working correctly, require rigorous testing and inspection. Examples: structural analysis of gear drive, thermal analysis of brakes, flow analysis of a heat exchanger, and electromagnetism analysis of a motor, to name a few. Following our example of a system which can easily solve using analytical technique, which include a bar under axial tension, free damp vibration system, and axisymmetric fluid flow. However, complex systems like fluid flow through a heat exchanger cannot be solved analytically, even though we know the governing differential equations, which is the well-known Navier-Stokes equation. It is one of the Millennium Prize problems. This is because it is very complex to analytically solve Navier-Stokes equation. Until now, no one has proved the analytical solution of the equations. Thus, for such cases, we must rely on numerical methods. Let's look at what finite element analysis. All numerical or simulation methods include three basic steps, which are pre-processing, processing, and post-processing. Pre-processing in finite element analysis includes modeling the geometry of the given problem, which entails creation of 3D or 2D model. Then discretization means dividing the geometry into parts which are called as elements, and applying the necessary boundary conditions, which reflect the physical conditions. Processing include selecting the appropriate solver methodologies for the solution. Post-processing include visualization of results with the help of graphs, contours, vector plots, which can be used for validation. Now let's discuss why do we need FEA. Many physical systems can be solved analytically under some assumptions, but real life scenarios can be totally different. And even the analytical solution exists, but it's very complicated to solve and time consuming. So from the geometry to boundary conditions can be significantly different and complex from standard or conventional values. The materials and their properties can have nonlinear behaviors, but also they can be inhomogeneous or anisotropic. Another important reason to use FEA or any other simulation technique is that the experimental analysis sometimes may not be feasible and can be too costly, and thus FEA is the only solution in that case. The most important advantage of the numerical methods is that it provides solution over the whole domain, which means the value of any parameters can be found anywhere inside the domain, which is not possible by experiments. So when to use FEA, most of the problems have solutions which are obtained from correlations based on experiments or some other techniques, and hence may not require FEA approach. But Same problems under some critical conditions have to be solved using FEA. Example nozzle design and pressure vessels have ASME standards, but when two nozzles are placed close to each other, they may cross critical limit, which requires FEA approach. Let's summarize what we discuss in this video. FEA is numerical method which approximates the solutions. Not all differential equations can be solved, hence the need of FEA arises. Complex geometries, material properties, loading conditions can be modeled using FEA, provides solution over whole domain, and can easily calculate any parameter, avoid or optimize set of experiments. We can use design conditions away from standard codes, and the following are the reference you could look at for further reading. And that's all for today's video. For any doubt or suggestion, do not forget to comment. Thank you.